Hello, Math 201 students. We're looking at section 2.3. 2.3 is finally going to give us the precise definition of a limit. So we've been talking about limits. We've gotten kind of a good conceptual grasp of it. In fact, we have a pretty much as good a grasp and language on limits as Newton and Leibniz had back in their day. But since the days of Newton and Leibniz, the language and the definitions that we talk about in calculus have been refined and have been improved so that they are given a precise definition which is going to be given in this unit. Now there's going to be a lead up to it. So the things we're going to talk about first may seem kind of weird, but they are all to lead up to this true, precise definition of a limit. All right, so we're going to replace the vague expressions like gets arbitrarily close, or what I like to say is gets closer than you can possibly imagine, in the informal definition with specific conditions that can be applied to any particular example. With a precise definition, we can avoid misunderstandings, prove the limit properties given in the preceding section, and establish many important limits. To show that the limit of f of x as x approaches c equals the number L, we need to show that the gap between f of x and L can be made as small as we choose if x is kept close enough to c. Let us see what this would require if we specified the gap, the size of the gap between f of x and L. So in other words, instead of just saying as small as we choose or close enough, we're going to specify. And these examples aren't getting there yet, but they're getting us closer. We're going to specify a certain tolerance, a certain distance that we have to get close enough to establish the limit. But again, this example is just going to give some numbers here. Consider the function y equals 2x minus 1 near x equals 4. All right, so here, let's look at this graph. This is the graph of y equals 2x minus 1, okay, near x equals 4. So near x equals 4, we kind of obviously already know what this answer is, but near x equals 4, y is going to be near 7. In fact, it's going to equal it. When x is 4, y is 7, we already know that. If we plug in 4, 2 times 4 is 8, 8 minus 1 is 7. And here's the point, 4, 7. But we're trying to get more calculus-y than that. So as x gets close to 4, y is getting close to 7. All right? And so we know that the limit as x approaches 4 of 2x minus 1 is 7. And it's obvious that that's the case. However, how close to x equals 4 does x have to be so that y equals 2x minus 1 differs from 7 by, let's just say, less than 2 units? So, all right, let me see if I can say that a little bit more clearly. How close to 4 does x need to be so that we satisfy this condition? And we just kind of made this up. We made this condition up. The condition is that y has to be within 2 units of 7. So if the y value has to be within 2 units of 7, if that's the condition, how close does x need to be to 4 to meet that condition of y being at most 2 units away from 7? Here's a graphical picture of that, okay? Y being within 2 units of the value 7 would mean it could be between 5 and 9. So here's that picture between these two red lines here, this yellow region. And we can see graphically that to be that, we just come up here. Here's kind of the 2 endpoints of that region along this line, so that we can see graphically that if we want y to be within 2 units of the value 7, x is going to need to be between 3 and 5. If x is greater than 5, then we're out here. We're beyond 9 for the y value. If x is less than 3, we're over here, which means we are beyond or less than 5, which would not satisfy the condition we laid out. All right, so let me work that out algebraically. Okay, so here's our problem, y equals 2x minus 1, and we want to choose values of x such that y is going to be within 2 units. It's going to be less than or equal to 2 units away from 7. What values of x satisfy that condition? All right, let me go back to my problem and show you how they worded the question. I just reworded the question in a way I think you could understand better, but here's how they worded the question. How close to x equals 4 does x have to be so that y, which equals 2x minus 1, differs from 7 by, say, less than 2 units? Okay, let's go back to it. Y differs from 7. So y differs from 7. If you want to say y, the difference between y and 7, you say y minus 7. And if we're saying that y differs from 7, that means it could be on either side of 7. It could be up to 9 or down to 5, which the way to take care of that is to use an absolute value symbol. That means that the difference between y and 7 on either side is what we're looking at. So use the absolute value symbols, which means y is y minus 7 or 7 minus y. Either one of those would work. And we want that to be less than 2 units. Or I could even eliminate that or equal to. We just want it to be less than 2. So it's within 2 units of the value 7. All right, now what is y? Y is 2x minus 1. So I'm trying to figure out what values of x satisfy this. So if I'm trying to figure out what values of x make this happen, then I'm going to substitute this expression with x in it. I'm going to substitute that in for y. Since this is equal to y, I can do that. So now I've got the absolute value of 2x minus 1 minus 7 is less than 2. Okay. Now just simplify a little bit. Sorry. The absolute value of 2x minus 8 is less than 2. And now, hopefully you've had some absolute value problems before, and so you know what's going to happen next. But if you don't, what we're saying is that 2x minus 8. Okay, let me just show you. If we keep in mind that the absolute value truly means the distance from 0. So here's 0, here's 2, here's negative 2. We're saying that whatever's inside of this absolute value is less than 2 away from 0. So it's in this region here, somewhere in that region there. Okay, so that means we're saying that we're saying 2x minus 8 is less than 2 while also being greater than negative 2. 2x minus 8 is between negative 2 and 2. That's what that absolute value means. The absolute value of 2x minus 8 being less than 2 means that it's less than 2 units away from 0. So that means 2x minus 8 is between negative 2 and 2. And then solve for x. So add 8 to both sides. Or when I say both sides, I should say all 3 sections. And we get 6 is less than 2x is less than 10. Now divide all the sections by 2. And we get x is greater than 3 and less than 5. And we have just answered the question. What question did we answer? Let's remind ourselves. Let's go up here and put the answer down. X is between 3 and 5. And what did that mean again? We're answering this question. we want y to be less than 2 away from 7. What values of x make that happen? Well, when x is between 3 and 5, y is less than 2 units away from 7. When x is between 3 and 5, y is between 5 and 9. And let's go back and look at it graphically again. When x is between 3 and 5, y is between 5 and 9. Another way we could say the answer is when x is within 1 unit of 4, y is within 2 units of 7. All right. Now, why did we even care to do a problem like that? Again, it's building up to a precise definition of a limit. It's just kind of doing it as a concrete example before we get to the very abstract or theoretical definition we're about to get to. All right, in the previous example, we determined how close x must be to a particular value c to ensure the outputs f of x of some function lie within a prescribed interval about a limit value L. So kind of saying the same thing. As x approaches c, so x is within some values of c to make y approach L. In other words, to make y be within some given value of L. To show that the limit of f of x as x approaches c actually equals L, we must be able to show that the gap between f of x and L can be made less than any prescribed error, no matter how small, by holding x close enough to c. Again, my country boy way of saying that is that whatever value we can imagine that is as close to c as we can imagine, there's always still a closer one. So whatever we say as far as I can imagine x getting this close to c, which would make y get this close to L, you can always still find a value that's even closer to c for x. That would make y get even still closer to L. And that's how we're getting toward the understanding of a limit. Definition of a limit. Suppose we are watching the values of the function f of x as x approaches c without taking on the value of c itself. Certainly we want to be able to say that f of x stays within 1/10 of the unit from L as soon as x stays within some distance delta of c. But that in itself is not enough, because as x continues on its course towards c, what is to prevent f of x from jittering about within the interval from L minus 1/10 to L plus 1/10 without tending toward L? We can be told that the error can be no more than 1/100th or 1/1000th or 1/100,000th, but each time we find a new delta interval about c, so that keeping x within that interval satisfies the new error tolerance. And each time the possibility exists that f of x jitters away from L at some stage. The figures on the next page illustrate the problem. You can think of this as a quarrel between a skeptic and a scholar. The skeptic presents the Epsilon challenges to prove that the limit does not exist, or more precisely, that there is room for doubt. But the scholar answers every challenge with a delta interval around c that keeps the function values within epsilon of L. Ooh-wee, that is some serious jargon, some serious abstract talking right there. Let me see again if we can just calmly think about what we're trying to say here. So we're saying, let's go back to the line to get more concrete with it. All right, we already know that this line, if we plug in 4 for x, we get 7 for y. So when that's the case, the limit is easy. It's just equal to whatever the function is equal to. But it might, but that's not always the case. So we don't even care that when we plug 4 in for x, we get 7 for y. What we care is that when we plug in something unimaginably close to 4 for x, we get something unimaginably close to 7 for y. So all right, I really like the language they use about this skeptic and scholar. All right, the Greek letter delta symbol that was in that we're getting toward in this definition is the distance that x is away from c, or whatever value you're talking about for x. The epsilon is the y value, the distance that y is from L, or from whatever this y value is, the limiting value. So we've just, let's say the skeptic just produced this doubt, and he said, well, if you get within 2 units of 7, you don't know that it might not jump around and be not close to, not close to 7 here. It might go beyond that. It might go higher or lower. And so the scholar then says, look, I'm going to find for you, I'm going to answer your doubt by finding values of x, values for the delta here, the distance from this c value. I'm going to find these to make sure that we are going to be within 2 units of 7. And so the skeptic might say, that's not enough. You haven't proven it. I want it to be within 1 unit of 7. And so then the scholar would have to find new delta values that would ensure that the y values were within 1 unit of 7. And then the skeptic would say, well, that's not enough. I want you to, we need to be within 1/1,000,000th of a unit of 7, from 7. So then the scholar would have to produce delta values near 4 to say, if I'm this close to 4, we are within 1/1,000,000th of 7. And what's going on here now is that the skeptic can always think of a closer doubt, of a closer, more precise thing that you have to prove in order to prove that his doubt is wrong, or his doubt is answered. But whatever doubt he poses, we're always going to be able to find an answer to make it happen. He's going to imagine getting closer and closer, and we're going to answer it every time by getting closer and closer to 4. And when that happens, when that condition is met, when whatever he says, whatever limiting tolerance he wants, we can always find one to match it. When that's the case, you have a limit. You have a limiting value when that's the case. And when you don't, when you're not able to provide that, then you don't have a limiting value. The limit does not exist in that case. All right, here's an illustration. So the skeptic says, I bet you can't get it. Bet you can't get it to within 1/10 of a unit from L as x approaches C. And so the scholar answers him, bet I can. And he finds this delta value that gets the values of x to within 1/10 of a unit of the limiting value L. So the skeptic says, I bet you can't do it to within 1/100th. And he finds these delta values that get him to within 1/100th. And the skeptic says, what about 1,000th? And he finds those. What about 100,000th? And he finds those. Look, we're narrowing it down. And so the skeptic thinks of a new challenge. And he constantly can do that. So what we do is we make whatever the skeptic wants to say, since it can be whatever, let's make it a variable. And so we make it this Greek symbol called epsilon. All right, bet you can't get to within epsilon of that limiting value L. And the scholar says, bet I can. I'm going to find the delta. So the delta is the Greek letter that we saw earlier. I'll have to show you again. Delta is this thing here that gets you to within that. All right, let's go back over here. So here's that symbol for delta. I usually don't make it that fancy. myself. I'll show you how I make it in a second. All right. How do we stop the seemingly endless series of challenges and responses? We can do so by proving that for every error tolerance epsilon that the challenger can produce, we can present a matching distance delta that keeps x close enough to c to keep f of x within that epsilon tolerance of L. This leads us to the precise definition of a limit. Here is your precise definition of a limit that was about 1800 years in the making. Let f of x be defined on an open interval about c, except possibly at c itself. We say that the limit of f of x as x approaches c is the number L, and write the limit as x approaches c of f of x equals L if this is the only way that you can do this, only way that we can legitly say that this is the case, if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x, for any possible x value, the distance of x from c is between 0 and delta, leads to the distance of f of x from L being less than epsilon. Epsilon is the challenge, delta is the answer to the challenge that makes it happen. Or you can say 0 is less than the absolute value of x minus c, which is less than delta, implies that, or in other words, accomplishes or produces that the fact that the absolute value of f of x minus L is less than epsilon. I know this is very deep, this is very hard to grasp, I totally get it. Some of you might be able to grab a hold of what's going on, and some of you may be struggling, but when we get down to the nitty-gritty of doing problems, you're going to be able to see how the problems are done step by step. So don't panic. One way to think about the definition is to suppose we are machining a generator shaft to a closed tolerance. We may try for diameter L, but since nothing is perfect, we must be satisfied with the diameter f of x somewhere between L minus epsilon and L plus epsilon. The delta is the measure of how accurate our control setting for x must be to guarantee this degree of accuracy in the diameter of the shaft. Notice that as the tolerance for error becomes stricter, we may have to adjust delta. That is, the value of delta, how tight our control setting must be, depends on the value epsilon, the error tolerance for the diameter of the shaft. All right, so here's again the picture we're talking about. The value of y or f of x must lie within this epsilon region, and we have to find this delta region that accomplishes that. Okay. Examples. The formal definition of limit does not tell us how to find the limit of a function, but it enables us to verify that a conjectured limit value is correct. The following examples show how the definition can be used to verify limit statements for specific functions. However, the real purpose of the definition is not to do calculations like this, but rather to prove general theorems so that the calculation of specific limits can be simplified, such as the theorem stated in the previous section. We've already seen this. Example 2 now. We finally get to a concrete example again. Show that the limit of 5x minus 3 as x approaches 1 is 2. All right, we're trying to show that the limit of 5x minus 3 as x approaches 1 is 2. We kind of already know this to be true, obviously, because if you plug 1 in, you get 5 minus 1 minus 3, which equals 2. So it's obviously going to be the case, but we have to show it and prove it. We're going to use our definition of the delta epsilon definition of a limit that we were just reading. So that says that we have to have this to be the case. That the distance between x and 1 must be within some delta, right? It's between 0 and delta. has to be less than delta, implies that, in other words, if we're finding that x value, that implies that the distance between f of x and 2 is less than epsilon. So this implies this. We have to find it. We have to find that accomplishes that. All right, let's see if we can make some magic happen here. All right. So we're trying to find this. This is what we're trying to find. We're trying to find a delta that makes this happen. All right. So we're going to do that by starting here and working back to delta. Start there. So what is f of x? F of x is 5x minus 3, right? That's what f of x is. All right, so we got the absolute value of 5x minus 3 minus 2 is less than some epsilon value. Okay. Simplify. Absolute value of 5x minus 5 is less than some epsilon value. All right, here's where we're going to do a little trick here. Look at 5x minus 5. If I can make that become x minus 1, then I have found my delta, because x minus 1 is what is less than delta. And so I have found my delta in terms of this epsilon, and that's what I'm trying to do. I want to get delta in terms of epsilon, and that will do it. That will answer every question from the skeptic, because then whatever he gives me, I've got a delta in terms of what he just asked. In other words, the answer will be in his question. So watch this. If I factor out a 5, that leaves me with x minus 1 less than epsilon. Then divide both sides by 5, so that I now have the absolute value of x minus 1 is less than epsilon over 5. And because the absolute value of x minus 1 is less than delta, then epsilon over 5 can just be my delta. We just found it. Now, there may be deltas that work better, that are closer, but that's not the challenge. The challenge is not to find every delta or the perfect delta. It's just to find any delta that will answer any epsilon. And we just did it. Whatever epsilon that joker gives us, we now have a delta that will answer it in terms of the question he asked. So if he says, get it to within a millionth, then it's just a millionth over 5. And whatever, and now it's in an abstract. The good thing about abstraction is it proves things for any case. Arbitrarily close. Whatever you do your worst, skeptic, and I will have the answer, which proves beyond any shadow of doubt, because it proves it for every instance that this is the case. And that's the power of the epsilon delta definition of a limit in these abstract terms. It truly does prove it for any case. All right, now we've seen these before. These were presented as theorems in the previous section, but now we're going to prove them using the delta epsilon definition. So I'm going to prove part A right here. I'm trying to find a delta such that x minus c is less than delta, implies the fact that f of x, or sorry, I don't have to write f of x because I'm given the f of x. The f of x here is just x. That x minus, and here's c. So this c is where that one came from, and this c is where this one comes from, and this x is where that comes from. It's kind of confusing here because they're kind of all so similar, but that's why this one is kind of a simple thing. The limit of the function f of x equals x as x approaches c is just going to be c. That's, f of x equals x means the y and the x value are the same, like the points 1, 1, and 2, 2, and 3, 3, and 0, 0, and negative 5, negative 5, and so on. X minus c is less than epsilon. This one is extremely simple because it's already solved. Look, x minus c is less than delta. X minus c is less than epsilon. That means that the delta and the epsilon can just be the same. We can just simply say this means that the answer to my question, the answer to the skeptic's question, is simply the fact that delta just will equal epsilon. Since x minus c is less than epsilon and x minus c is less than delta in this case, then whatever epsilon the skeptic poses, the delta can just be the same value as that epsilon, and that proves it. All right, let me try part B right here. This time 0 is less than the absolute value of x minus c is less than delta, implies that the absolute value of k minus k is less than epsilon. All right. This one's going to actually be very simple. What is k minus k? It's just 0. The absolute value of 0 is less than epsilon. Well, when is 0 going to be less than some other number that's not 0? All the time. All the time. In any case, under any circumstances, this is always true. Always true. That 0 is less than some positive number epsilon is always true. No matter the delta. Which means delta can be any number, is any positive number. Delta is any positive number. Choosing any delta that we want will always answer the skeptic in this case. The skeptic did not pose a very hard question for that. All right, look at these last two examples graphically. Here's the line y equals x, right? So whatever this epsilon distance is, you find a delta that is equal to that epsilon, and it's going to make this happen. As long as, so let's come back to the y equals k. All right, to get with an epsilon, it doesn't matter whatever epsilon is. Delta can be anything. Like you can make delta be in a billion, and you're still going to be within epsilon of that value k. All right, let's try example 4. Let's read about example 4. In examples 2 and 3, the interval of values about c for which f of x minus L absolute value was less than epsilon was symmetric about c. And we could take delta to be half the length of that interval when such symmetry is absent, as it usually is, like in a curve. We can take delta to be the distance from c to the interval's nearer endpoint. Okay. All right, example 4. For the limit as x approaches 5 of the square root of x minus 1 equals 2, find a delta greater than 0 that works for epsilon equal to 1. So he's given us a concrete example here. I mean, a concrete number for epsilon, not instead of just leaving it as an abstract number, which is going to lead us to another example where he does make an abstraction. For this example, we have a specific goal for epsilon equal to 1. That is, find a delta such that for all x, the distance between x and 5 is less than delta, accomplishes the fact that the distance between the square root of x minus 1 and 2 is going to be less than 1. All right, so the first thing we will do is we will simplify that down and solve it, and then work backwards to delta. Let me come up here and do that. It's the square root of x minus 1 minus 2 is going to be less than 1, but also greater than negative 1. Now I'll add 2 to both sides, to all three sections, that is. Add 2 to here, that'd be 3. Add 2 to here, that'd be 1. And then I'm going to square all the sections. That's going to give me 1 is less than the square root of x minus 1, which is less than 9. Oop, I don't have a square root anymore. Remember, it canceled out. Okay, and then I'll add 1 to all three sections now, and I will get 2 is less than x is less than 10. So I have my interval now for x. And I'm trying to center at 5 or around 5, because that's my x approaches. That's what I'm getting closer and closer to with x. So, all right, let's just look at that. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 2, there's 5, and there's 10. All right, so we want to choose the endpoint that's closer to the 5, because that will kind of go above and beyond what we need to do. So I'm going to choose the 2 for that reason. So that being the case, then my delta that accomplishes that particular epsilon of being 1, my delta is this right here. In other words, delta is this distance from 5 to the nearest endpoint. The delta is going to be 3. That will always accomplish the epsilon being 1 or better than 1. Okay. This leads us to, let me just show you that before I get on to something else. This is the graphical illustration of what we just did algebraically. See, this is a curve, so it's not going to be a centered square thing. So here's 5, and if we want to be within 1 unit of 2, that takes us all the way out here and all the way down here. But if we want to find the delta that accomplishes it, we wouldn't go all the way to the endpoint of 10, because that's 5 away. And that, if I was 5 away, that would not work out here, because then I would get outside of that epsilon limitation, that epsilon condition. It would be more than 1 away from 2 if I'm down here, right? So that's why I take the lesser, the closer of the 2 endpoints, so that my delta then will be 3, because the closer endpoint was 3 away from 5. And so it puts you a little closer than you need to be over here, but that's okay to be. It's okay to be closer than you need to be, but it's not okay to be farther away than you need to be. All right, which brings us to kind of this nice explained algorithm, this explained process. How to find algebraically a delta for a given function, limiting value L, C which x approaches, and epsilon greater than 0. The process of finding a delta greater than 0 such that for all x, we've already said this so many times, but the distance between x and c is less than delta, and the distance between f of x and L is less than epsilon, can be accomplished in 2 steps. Step 1, solve the inequality absolute value of f of x minus L is less than epsilon. So this part, solve this part to find an open interval a to b containing c on which the inequality holds for all x not equal to c. So in other words, solve this thing first. All right, and that's going to give you this interval, which this interval is, that's kind of what we found, 2 to 10. The interval from 2 to 10, that's what we found in the previous example. Next, step 2, find a value of delta greater than 0 that places the open interval c minus delta to c plus delta centered at c inside the interval a to b. The inequality f of x minus L less than delta will hold for all x not equal to c in this delta interval. That's picking this centered interval that's centered according to the closer endpoint. So it's centered at 5 and it's based on the closer endpoint of 2, so that we're now 3 away from 5 on both sides. So the delta is 3. So x between 2 and 8 will make y be between 1 and 3. All right, example 5. Prove that the limit of as x approaches 2 of f of x equals 4 if f of x is defined by this piecewise function. So look, here's this piecewise function. F of x equals x squared as long as x doesn't equal 2 on this particular piecewise function. So it is this parabola, except here when x equals 2. At x equals 2, it is not this parabola. It is simply f of x equals 1. So it is this point when x equals 2. It is the point 1. It is the point 2, 1. So it is happy to be this parabola until it gets to 2, and then it is no longer happy to be that parabola. It now is defined at that point. Then after that, it is happy to be that parabola again. But we're trying to prove that the limit of this function as x approaches 2 is 4. So this function gets close to 4 as x gets close to 2. I kind of have to start this way. I don't know why, but I kind of always have to start with this definition. Okay, so I'm going to start with this guy. And what am I putting in for f of x? All right, I don't care what it is when it's equal to 2. I don't care about that. I only care about what it is near 2. And this is what it is near 2, right? So I've got the absolute value of x squared minus 4 being less than epsilon, which means wherever epsilon is, okay, the distance that this is from 0 is between negative epsilon and epsilon. That's what absolute value means. It means the distance from 0. So it's somewhere in there. So here's how I set that up. I say x squared minus 4 is both greater than negative epsilon and less than positive epsilon. And I solve both. I solve the whole thing, I mean. I'll add 4 to both sides. That gives me 4 minus epsilon is less than x squared, which is less than epsilon plus 4. And then I take the square root of all the sections. That gives me the square root of 4 minus epsilon is less than x is less than the square root of epsilon plus 4. So that means I have this wherever c is, okay, on the x-axis. Wherever c is, I now have an interval. I have the square root of 4 minus epsilon, and I have the square root of epsilon plus 4. The question is which one is going to be closer to c, right? So In fact, I don't even have to write C. I actually know what C is in this case. C is 2. X approaches 2. So now the question is, which one of these is closer? All right, so I'm trying to figure out, is 2 minus the square root of 4 minus epsilon versus the square root of 4 plus epsilon. So I could write that as epsilon plus 4 or 4 plus epsilon, right? Minus 2. Which one is bigger? Or which one is smaller? I want the smaller one, right? I want the smaller distance. All right, so let me just think about this for a second. Epsilon is something that's a little bit more than 0. So the square root of 4 minus something a little bit smaller than 0 would be something a little bit less than 4. The square root of something a little bit less than 4 will be something a little bit less than 2. So 2 minus less than 2 would be, it would be 2 point something. Right? All right, what about over here? Square root of 4 plus epsilon. So that's going to be something a little bit more than 4, which would give me something a little bit more than 2. So more than 2 minus 2 would still give me 2 point something, right? Something a little more than 2. So so far I can't really tell which one of these is closer to 2. I'm having trouble finding which one of those is closer to 2. So, but what I can still accomplish what I'm trying to accomplish in the problem by saying that delta is equal to the minimum of 2 minus the square root of 4 minus epsilon and the square root of 4 plus epsilon minus 2. So it's saying we found the delta. We don't know which one it is, but it's one of these. Definitely one of those. So there is, in other words, we found that there is a delta and it does exist, and it's either one of these. So it's whichever one of these is smallest. Which, even if we can't tell, is fine. We still prove that it exists and that there is one, which then proves that to be true. I truly, truly know that this is extremely complicated. Like, it is so complicated, it is hard to understand what is going on. It is not what we will do for most of this course. There will be a lot of good practical application problems once we get to derivatives and when we're taking them, and there's going to be a lot of good problems. This is just the foundational theory that we're going to have to create in order to build upon it. So again, don't panic if this is too high for you to reach. I totally understand that. It almost is for me too, and it is for most people in the world. But if this does kind of spark an interest in you about what mathematical theory is and what it can do and the power of it, then take some graduate math courses at some point in your life. And by the time your kind of brain has matured even more than it currently is, you'll be able to handle this even a little bit better. But I truly get it that this is hard to grasp, and I don't blame you for that. If you feel that way. In fact, the stuff that we just covered is beyond what most calculus classes require as well. But right now I'm just going to do some of the homework problems from section 2.3 so that you'll kind of feel confident about what you're doing on that assignment, so that you can make sure that you're still succeeding on your grades. All right, number 1, suppose that the interval a to b is on the x-axis with the point C inside that interval. For the given values of a, b, and c, find the value of delta such that for all x the distance between x and c is less than delta implies that x is between a and b. All right, let me draw that for you. All right, let's draw it. So here we go. So here is a equals 8. Here is b equals 20. And here is c equals 17. So the question is what delta value will ensure? All right, so what delta value will ensure that x stays between 8 and 20. All right, so the distance between x and c is less than some delta. What delta value will ensure that x, which is some distance away from c, what delta value will ensure that it stays between 8 and 20? All right, well, you're going to base that on the closer endpoint, right? Like you couldn't say, well, I mean, what value of delta going away from c will ensure that we stay within between 8 and 20. Since 20 is closer, use that. This would be the delta. So it's really simple. What is delta? Delta is 3. That will ensure that we stay. I mean, even if we go this way by 3, that would put us at 14, right? So we certainly wouldn't use 8, because then it would be 9. But if we were 9 away on this side, we would be beyond 20. So it wouldn't work. So we're going to use the closer endpoint to help us solve that. So delta equals 3 will do that for us. Now it could be closer than 3, but delta equals 3 it just does enough to accomplish what we're trying to do. You can see number 4 that this one is quite simple. The value of delta that accomplishes this particular value for epsilon is just the distance from 5 to either one of these things. And since it's a linear thing, they're both symmetrical around 5. So it would simply be 0.025 for the answer there. Whichever way you go, whether you go to 4.75 or 5.25 away from 5, then you're 0.025 away. All right, here, because we're a curve, we may probably are not going to be symmetrical around that value. So the c value is 2. And the a value would be the square root of 3. The b value would be the square root of 5. And we're trying to figure out what delta value would make it stay within there. What's the largest value of delta that would still be within that interval? And we're going to have to subtract that. We're going to have to say 2 minus the square root of 3 versus the square root of 5 minus 2 and figure out which one is greater. So use your calculator. Figure out which one of these is the smallest, and that's what you want. Okay, so I calculated this, and I calculated this one to be about 0.268, and this one to be about 0.236. So this is the one we want, and so this is the delta. That's the largest delta that still accomplishes that. If we chose this one, it would not accomplish this. It would be outside of that range on one side or the other, even though it would still be inside on one of the right here, it would be outside of it up here by just a little bit. So you're always choosing the smaller difference here for your delta. All right, number 6. We're just doing our delta epsilon for the given values. It gives me L, it gives me C, it gives me epsilon. So I'm going to do, so let me just say this. This is proving that the limit as x approaches 5 of the square root of 8x minus or plus 81 equals 11. That's what we're trying to prove. Okay. And we're going to follow what it said to do in the book before. We're going to first solve this. I don't have to put f of x. I'm just going to go ahead and write what f of x is, which is the square root of 8x plus 81. Minus 11 is less than 0.09. And I'm going to solve that. So negative 0.09 is less than the square root of 8x plus 81 is less than positive 0.09. Square all the sides. And we get, sorry about that, I realized I wrote it wrong. So let me try writing it again. If I can get my hand to work correctly. Negative 0.09 is less than the square root of 8x plus 81 minus 11. That's the part I left out when I wrote it down the first time. 0.09. So now, first I would need to add 11 to all three parts. And so that gives me 10.91 less than the square root of 8x plus 81, which is less than 11.09. Then I will square all the sections, and that will give me 119.0281 is less than 8x plus 81, which is less than 122.9881. Then I'm going to subtract 81. That gives me 8x. It's going to be 41.9881. And over here it's going to be 38.0281. Now divide by 8. Get 4.75. That's just rounded to that. We get 5.25. Let's round it to that. So we now found our x, and we need to use the c I think because they're both the same distance, I think I need to round this to a further out, a more precise number. This is 0.246485, and this one is 0.2. No. I wrote it wrong. Okay, let's try again. This is 4.7535125, and this one is 5.2485125. And so now we're going to use the c equals 5 here to figure out which one of these is closer to 5. So I'm doing 5 minus that. I'm doing that minus 5. And so here I get 0.246485, and here I get 0.2485125. So this one is closer. And that is the delta then. This is the delta. The largest open interval. Let's now answer the questions. Maybe it'll lead us to the questions. The largest interval about C, on which the interval holds, is these two numbers. Negative 4.7535 to 5.2485. Okay. So let's go back to problem and try to enter those answers. Use interval notation. 4.7535. This is round to 4 decimal places. 7535, comma. The other one's 5.2485. 5.2485. All right, that does it. So the delta is what I showed you before, which is 0.0465. Good deal. All right, for number 9, for the given function, the point C and the positive number epsilon, find L equals the limit of f of x approaches C. Then find the number delta greater than 0 such that for all x, this whole limit definition holds true. So finding L is simple here. Just plug 3 in for x, and that should give you L. And then the rest of it would be just like the example we've already shown. Here, similarly, finding L in this case, though, if you plug in 3, it won't be possible, right? Because that's going to make the denominator be 0. So what you're going to want to do here is factor and simplify this expression to find another expression that is the same as this one except at 3. And then you can plug 3 into that one to find the value of L. All right, here we're going through the whole epsilon delta proof in parts. So we want to do the absolute value of f of x minus L. So that's going to be 3x plus 2 minus 2 to be less than epsilon for any x minus 0 less than delta. So let's simplify that. 3x plus, that's just going to be 3x. Absolute value of 3x is less than epsilon. By the way, this simplifies as well. It just simplifies the x is less than delta. And watch what's going to happen here. If I factor out of 3, then divide by 3, notice this is the absolute value of x is less than something, and this is the absolute value of x is less than something. So that means we can take the delta and say therefore there is a delta related to epsilon. The delta can just be epsilon over 3. All right, so that's it. So we chose choice D there for that problem, and it is correct. Well, let's go through number 12 here. All right. To prove the given limit statement, it is necessary to show that for all x, if 0 is less than x minus something, absolute value is less than delta. So it's just seeing if you are familiar enough with what we've talked about to fill in the right things. it's x minus c. In this case, the c is 0. So x minus 0. Then f of x minus what? F of x minus L. In this case, the L is 2. 2. This is just taking us through the delta epsilon proof, and it's just making us fill in a few things along the way. It says solve this inequality to find an open interval about c equals 0 on which the inequality holds for all x not equal to c. So it does that step for us. It breaks it down to that thing, and then it breaks it down to the negative epsilon is less than that thing, and it's less than epsilon. So then it wants us to fill in something in this next step. What would we do in the next step to solve this? We would add 2 to both sides, right? So if you add 2 over here, it'd be negative epsilon plus 2, or you could say 2 minus epsilon. If you add 2 over here, what would it be? It would be epsilon plus 2. And there's the epsilon button for you. Or you could even do a little / EPSILON, and it does the little epsilon symbol for you that way as well. Plus 2. Then it does the next step for you, squaring all the sections. Then what does it do next? It makes you fill in this side, which is just going to be, what will you do next? Just subtract 4 from all the sections, right? Subtract 4 from all the sections. Well, actually it doesn't. In this step, it hasn't subtracted 4. It's just, all it's doing is expanding the 2 plus epsilon, or in this case, expanding the 2 minus epsilon squared. So 2 minus epsilon times 2 minus epsilon. So that would be 4 minus 4 epsilon plus epsilon squared. So these steps, I like the way it's doing this because these steps are not really that hard to accomplish. In fact, you don't even have to really totally understand a whole lot of the entire concept. You're just filling in some things, which is just doing some algebra to fill in those things. So the next thing it does for you by subtracting 4 from all sides. If it subtracts 4 over here, the 4's cancel and the 4's cancel. Okay. Then the last thing you do here is divide by -1, which changes the signs. This becomes positive 4 epsilon minus epsilon squared. This would become negative 4 epsilon minus epsilon squared. Okay, then it says the inequality holds for all x not equal to 0 in the open interval, and here's the interval. That's one endpoint of the interval. That's the other endpoint of the interval. Actually, let me say that. Let me point out something that just happened that I didn't point out and I should have. When we divided by -1, what happens to an inequality when you divide by a negative? The inequality flips. So notice, and I didn't even notice this before, they flipped their inequality. So now x is greater than this one and less than this one. So this is the left endpoint. This is the right endpoint. So the open interval is from this value to this value. All right, now find a value of delta greater than 0 that places the centered interval inside the interval of that. Take delta to be the distance from c equals 0 to the nearer endpoint of those two things. So it would be 0 minus this, and this minus 0, because 0 would have to be inside of those two things. So we're taking the minimum of that and that, which simplifies down to 4 epsilon plus epsilon squared and -4 epsilon plus epsilon squared. What's the minimum of those two things? I believe that I can say that the minimum of those two things is going to be this, because epsilon squared is the same thing. But if we add a small positive value versus subtracting a small positive value, the one where we subtract the small positive value is going to be less than the one where we add the small positive value. So it's going to ask me on the next line, which one of these is it? Which one is the minimum? And we just talked about it. It's going to be this one. -4 epsilon plus epsilon squared. And that finishes up that, or does it? No, it's not finished yet, is it? Thus, if delta had a value of that thing, or any smaller positive value, the inequality automatically places x between these two things to make that hold true. Since there exists such a value of delta, the limit as x approaches 0 of that function is 2. In other words, you've just proven this in a rigorous mathematical way. Precisely. Wow. A lot of this stuff is kind of saved for math majors, which is awesome for some of us, but terrible for some of us too. So again, I don't blame you if you feel like this is too heavy. All right. This is going to do the exact same thing as the previous problem. This is going to do the exact same thing as the previous problem. This is going to do the exact same thing as the previous problem. Define what it means to say that the limit of g of x as x approaches 0 equals k. All right, this is another good question because it simply tries to see if you can take that definition of a limit that we've gone over and over and just apply it to this situation. What does the limit mean? It's definitely not a. Right? It doesn't matter that plugging 0 into g of x gives you k. It doesn't matter what it is. It matters what it's close to. All right, so let's see. All of these look the same at the beginning. So the question is, which one of these parts is correct? Well, it's not this one because it's the absolute value of x minus 0 in this case, which is just x, is less than delta, not epsilon. Implies that g of x minus k is less than epsilon. So it would be choice C. All right, I think that's probably enough of going over the homework problems with you for that section. Just again, I'll say it again, just know that this is going to get better as we go. There will be some good moments that are much better than these extremely complicated moments. So just hang in there. Good luck with 2.3 homework. Let me know if you need any help. I'll see you in the next one.